Yep, thanks. So I guess, so it's been 48 hours since I last talked, so maybe I want to just quickly recall what we achieved in the last lecture. So again, sort of the goal of the minimal model program is to do surgery operations to a foliated variety to either to transform the foliation into one where Kf is Nef, or transform it into a fiber space, which sort of looks like a P1 fibration. So we did this using a suite of 4 theorems. So I'll quickly recall what our 4 theorems were. So we had the cone result. So here we have, so I guess x, let's say, is KLT q factorial. But again, if you don't lose much of the flavor of things if you just assume x is smooth or even has quotient singularities. F, let's say, has canonical singularities. But again, this isn't so indispensable. And so what the cone theorem said was, well, if R inside the Kleiman-Mori cone is a KF negative extremal ray, then there exists a curve C inside X such that R is spanned by this curve. And we can say a bit more about what this curve is, but just to quickly refresh our basic ideas. So again, the idea is that if we have our Kleiman-Mori cone is, remember, it's the cone spanned by the homology classes, or the closed convex cone generated by homology classes of rational curves. And then, well, we have some hyperplane inside H2, which is divided in 2 by KF perp. Maybe it goes like this. And if it's negative on this side and positive on this side, well, if I have a ray here, then in fact, inside this ray, there's a curve C. So maybe somewhere in this ray. So this was the cone theorem. Again, it's just saying that if KF fails to be Nef, there's a reason for it to fail to be Nef, and that's going to be a particular kind of curve. The next result was the contraction result. So when we found this extremal ray, we could contract it. So we had a morphism x to y such that CR of sigma is a point if and only if the class of sigma was inside R. So the idea is that we have some birational morphism, or not necessarily birational, we have some morphism which is contracting every curve which appears in the ray R. Now, there were 3 possibilities for this contraction. Either this was a fibration, in which case we would stop. It could be a divisorial contraction, which is not such a big deal. Or it could have been a small contraction. So, and remember that if the exceptional locus of CR was codimension at least 2, so I guess CR is birational, and exceptional locus of CR is not a divisor, we ran into problems because if we just push forward the canonical bundle of the foliation to Y, so recall in this case that the push forward foliation, the canonical divisor is not Q Cartier in this case. It fails to be Q Cartier. And this is a significant issue because if it's not Q Cartier, we can't make sense of Nefness. So the solution to this conundrum was to produce what we called a flip. So then the flip exists So again, by definition, the flip is just some funny diagram. Oops. But remember that we had a very concrete example of a flip that we looked at, which was, so just to refresh, we blew up a P1 bundle at a point, and the example was we would flip this curve into the P2. So maybe to emphasize what was happening, just to quickly refresh things, we were flipping this red curve in the broken fiber into a section here. And this is the transform of P2. So this is some exception divisor. This is called E plus. Here was C. Here was C plus. So we had these things. We had these surgery operations called flips, which would fix things for us. And then the final result that we needed was termination, which said that there are no infinite sequence of flips. Oops. Okay, so we would put all these results together. And this would give us what we call a minimal model program. So starting with X, we would produce a sequence of birational maps, X to the n, such that one of two things happened. So such that, so we produce this infinite sequence such that either, one, we had a situation where there was a fibration xn to z such that minus kf is, so call this f, or minus kfn is f ample. So this was like our P1 bundle case from the surface world. Or kfn is nef. Okay, so this is a quick recap of what we talked about on Tuesday. I'll make just I'll make a few quick remarks before I go on. So remark one is that if kf, so just as we knew in the case of surfaces, we could tell at the very beginning which possibility we would end up in by just looking at the universal color of the leaves. So on a surface foliation, if the general leaf is uniformized by the disk or the complex plane, then we always end up in the case where kfn is nef. And in the remaining case, so the general leaf is a P1, then we would always end up in the P1 bundle case. So we remember from the surface case, we could always tell right off the bat which of these two possibilities we'd end up in. And the same thing is true in higher dimensions. So if kf is pseudo-effective, we always end in case 2. And if kf is not pseudo-effective, we always end in case 1. So there's never any mystery about which one we end up in. The other point I want to make is that this run of this sequence of surgery operations is not unique. So the model is not unique. At every step, we have to choose an extremal ray. So we have to choose some r. And the Cohen theorem doesn't tell us a preferred r to choose, so we have to make a choice at every step. So in particular, the outputs of the MMP are not unique. And so, but there is a lot that one can say about how different outputs of the MMP are related. So where I ended last time was just stating some of the cases where we knew these results. So if the dimension of X is less than 3, we know everything. So all four of these conjectures have a positive answer. So in dimension 3, we know everything. There's no mysteries. Now, if in the case where we have the foliation with one leaf, so TF is equal to TX, then we know cone, contraction, and flip, but we don't know termination. So termination is the hard part, but we don't. So what I wanted to start to talk about today, because this will be important when I talk about algebraically integrable foliations, is something called termination with scaling. So today, so the focus today is termination with scaling. And algebraically integrable foliations. Okay, so this is our game plan. So before I go on to talk about termination with scaling, are there any questions about this quick summary of what we've done, where we've come? Okay, great. So termination with scaling. So before I go into termination with scaling, I want to make a quick remark. And so I guess I want to emphasize, and I'll try to give a taste of this later on, that really the natural setting for the theory is to work with pairs. And actually, there's actually an even more general setting than that we should work with. But to work with pairs of a foliation together with a divisor, some Q. So this is an effective Q divisor. And our notions of singularities, et cetera, all make sense in this broader setup. So as we'll see, that the way a lot of these proofs work, hopefully I'll be able to explain some of these proofs, is by induction on dimension. And when you go through induction on dimension, pairs naturally arise as the proper framework for inducting on dimension. But they're also the proper framework for explaining termination with scaling. So let me explain now how termination with scaling works. Okay. So again, we're still in our usual setup. So X is KLT Q factorial, F is canonical. So let's let A be an ample divisor. And let's suppose that C is just some Q divisor. Such that KF plus A plus C is NEF. Okay. So the idea with scaling is that we're going to use this divisor C to choose our flips for us. So again, with the usual MMP, it was up to me or you to choose the flip, which is not necessarily a good idea because maybe we choose stupidly and we get into we choose bad choices of flips and so our process never terminates, hypothetically. The idea is that with termination with scaling, by choosing this divisor C, we're guiding our choice of flips and we make, hopefully, smarter choices. So what we want to look at is we define lambda naught to be the infimum across all t such that kf plus a plus tc is nef. And so it's a fact, or I guess it's essentially a consequence of the cone theorem. So the cone theorem, or conjecture as it may be, implies that there exists a kf negative, or a kf plus a negative extremal ray R such that kf plus a plus lambda naught c dotted with R was 0. So to give a quick picture of what's happening, so imagine this is, or maybe I'll write it like this. This is a chunk of our Kleiman-Mori cone. What we have is we have the ray. So this is the so this is kf plus a plus c perp. So again, this is just all those homology classes which have 0 intersection with k of f plus a. And then what we're doing is we're just scaling this linear hyperplane down until it touches that ray there. So then the idea is that we scale c a bit, and then we get to kf plus a plus lambda naught c perp. And now the idea with scaling is that this is the ray we flip or contract. Yes?
I know this is a legal question in a model code, but this is not a question. So which of these are devices and which of these are divisor classes?
Okay, so up here, so I really want my delta, well, okay, I really want my A to be an honest divisor.
Not just an class, but
Yeah.
not. Oh.
Yeah. So if we were in, there's a small subtlety here that okay, what I really want I want to treat A as a generalized divisor. This is what I'm really going to do. But for concreteness, I want to treat it as a divisor because the important thing is to apply the cone theorem to understand the singularities of kf plus a. I really need, or to apply the cone theorem to kf plus a, I really do need to treat A as some divisor.
But kf is a divisor class, right?
Yes, kf is just a divisor class. So yeah, kf, yeah. So there's, I mean, you have to choose kf on every model or something, and then.
And delta is an actual divisor.
Is a bona fide divisor.
And A is a generalized divisor. What on earth is that?
Yeah. So this is that's how I feel too sometimes, but. So that's a part of the story which I'm going to say absolutely nothing about, other than maybe this one comment here, just to confuse us all enough. But yeah, so I'll wave my hands about this a bit later. But please, yeah, think of A as being a bona fide divisor on X. So just choose. I mean, you have a lot of freedom to choose, but pretend it's a bona fide effective divisor, not just divisor class. Thank you. So yeah, I guess I also, there are lots of MMP people in the audience. So I guess if you're an MMP person, please raise your hand, and then you can bug these people also. I mean, there's Paolo there, so he knows all these answers. So, and of course, I'm happy to talk more about this after the talk too. But yeah, for the sake of keeping things conceptual and not too technical, we'll power on. But thank you for the question. So the idea with MMP with scaling now is this is the ray I want to flip or contract or do whatever with. So let's say x, call x x0, and let this be the contraction / flip associated to, and maybe let's call this R naught so this is our R naught contraction or flip. But now, what's true is that kf1 plus a1 plus lambda naught c1 is nef again. So if we call this map phi, I mean f1 is just the push forward of f naught, a1 is just the push forward of a, and c1 is just the push forward of c. So I get a whole new setup. But now this thing is nef still. So I can play the same game. So now what I want is I want lambda 1 to be the infimum of t such that kf1 plus a1 plus t c1 is nef. And I can just play the same game again. Yes, please. Yes, so yeah, I didn't say this last time, but divisorial contractions and flips preserve Q factoriality always. Yeah, thank you. And I guess I should also say that all these steps preserve KLT also. So KLT and Q factoriality is preserved by all these steps of the MMP. So now we can just play the same game. So we produce lambda 1. So what happens is we produce this infinite sequence of varieties. So xi, fi, ai, ci, and numbers, lambda 0, which is bigger than lambda 1, which is bigger than lambda 2, such that they all fit into this sequence of divisorial contractions or flips, and such that at each step I'm flipping the ray which was chosen by, so this one contracts / flips the k fi plus ai plus lambda I ci trivial ray. So the ray that was chosen for us by this scaling factor. And this is what we call an MMP with scaling. So this MMP with scaling. Okay, so no, not necessarily. So yeah, it could be the case that what happens, so potentially our Kleiman-Mori cone looks like, say, this, and then what happens is our supporting hyperplane looks something like this. So it's always going to be an extremal face, but yeah, there might be multiple rays. So you're right. I guess it's not really a complete panacea, but it does. So there is still some choice involved, but much fewer choices. And as we'll see, that somehow we cut down our choices enough in some sense. Okay, so as I rearrange these boards, are there any other questions? So I'll state another conjecture about all this stuff, and a theorem, and then I'll get back talking about foliations. Yeah, so the reason why I didn't want to just play with A, well, I could have, so a priori I could have just scaled with A at the beginning. The reason why is I lied a bit. So I'll tell you the lie I just made, and then you'll see why I want this more flexible framework. I started off the MMP with scaling with saying that A was ample. But after a single flip, A is no longer ample. So actually, that's a bit of a cheat. There's something I'm sweeping underneath the rug here about this fact. So A is no longer ample. So the right framework is this one. But yeah, thank you. So yeah, I lied to you guys. I apologize, but it is possible to make it all right but it takes a bit of extra technical complication. Conjecture is that flips with scaling terminate. So again, it's not clear that flips with scaling terminate, but so we have so somehow our full termination conjecture would imply this conjecture, and this conjecture is a priori weaker than the full termination conjecture. But there is a famous theorem of Bierk-Rakashini, Haken, and McKernan, which says that if either kx is big or delta is big, then flips of kx plus delta with scaling of an ample divisor terminate. So if you have some additional positivity, so either kx is big or your boundary is big, again, this is why it's important sometimes to work with a boundary, we can actually get termination of flips with scaling. To my knowledge, this is the best termination theorem that we know. And in practice, it's good enough for many applications. Okay. Any questions on this? So again, this is, so in most cases, so if, the takeaway from this in practice is that usually if you've set up your problem to work with termination with scaling, probably your MMP terminates. Or it's probably easy to kind of massage it into a form which terminates. Okay, so this is what I wanted to say about the machinery of the MMP. I want to change gears slightly now and talk about algebraically integrable foliations. So again, x, now I want x to be an arbitrary dimension. So on Tuesday, I was restricting myself to the case of a threefold. Now I want x to be arbitrary dimensional. And so we have a normal, again, a normal variety, f, a foliation, and I say that f is algebraically integrable if it is induced by a rational fibration. Rational vibration x to z. So i.e., the closure of leaves of f are exactly the closure of a general leaf of f is the closure of a general fiber of this morphism. Okay. So one very, I guess one easy case of an algebraically integrable foliation is the case of just a fibration. But of course, if you think about, let's say, like a pencil of curves on P2, a pencil of curves on P2 also defines it gives an algebraically integrable foliation. So, example, if f from x to z is a fibration, we get a well-defined algebraically integrable foliation. And even better, if f is smooth, so if we have a smooth fibration, then k of f is nothing other than k of x over z. But in general, these two divisors differ. So I guess on this one, it's a good exercise to compute k of x over z versus k of f. This is a good exercise. In fact, what's true is that k of x over z is k of f plus e in this example, or on this side. So this is a good exercise to just convince yourself that these things really do differ. And so in particular, well, okay, maybe I'll make another quick remark after this, and then another classic, a good class of examples is just pencils of say curves on P2. So these give obviously rational maps P2 to P1. These are other classes of examples. So on the heels of this example, I want to emphasize that so if you heard something about these about the minimal model program, you know there's something called the relative MMP. So given a fibration, there exists let's call it f from x to z. There exists a relative MMP. A fibration is, let's say, a contraction. So f star ox is equal to oz, and the dimension of z is smaller than the dimension of x. So I'm not assuming any kind of like flatness or whatever. Thank you. So there exists a relative MMP, which, and the goal of the relative MMP, it makes kx over z relatively nef. But in general, the foliated MMP will do something different. So I guess I want to make 2 points. So the kf MMP, because kf is not necessarily equal to kx over z, the kf MMP does different things. So it flips and contracts different ways, but also and this is a very crucial point, it makes kf globally nef. So you actually get a stronger conclusion in this case. So again, the relative MMP just tries to make the relative canonical bundle relatively nef. But the KF MMP, the output is actually something which is globally nef, not just relatively nef. So actually, again, I want to emphasize the KF. So even in this, in simple cases, they do different things.
And you might lose the vibration property.
Well, yeah, exactly. Yeah, a priori you can lose the vibration property precisely. So yeah, that's another important bit of flexibility with the foliated MMPs. You can really work with things which are not fibrations, where there's no way to run a relative MMP if you don't have a fibration to start off with. So you really do actually get quite a bit more flexibility. Thank you. Okay, so I'll tell you what we know about the algebraically integrable MMP. And then I'll tell you what we know, and then hopefully I'll be able to finally explain an interesting proof of something. We know. Okay. So the cone theorem, so again, just to emphasize, so our setup x is KLT q factorial. Again, this can be weakened a lot, so it's not so important. F is canonical. But again, you should think that really we should be working with pairs. So there's, again, I want to emphasize there's a whole more general story, whole more general framework where this is really happening. But for simplicity, let's just focus on this case, and then, okay, and also emphasize that F is algebraically integrable. So again, this is a foliation whose leaves are algebraic varieties. So the cone theorem comes from work with Ambro, Paolo, Shakurov, and myself. Actually, the reason, so I should say that we actually squeezed out some interesting geometric consequences, completely unrelated to foliations, out of the cone theorem for foliation. So I should say that there are, just to kind of advertise things, this has interesting geometric consequences in its own right, which are completely independent of foliation theory. So I just want to emphasize that there's some interesting geometry happening here. So it's just an advert, a teaser, but we won't go into it. So now with Paolo, we prove the contraction and flip theorem assuming termination with scaling. So this was something that Paolo and I proved. So again, if you take as a conjecture, if you assume this conjecture termination with scaling, which is, like I said, erased. So if you assume termination with scaling, we could prove existence of flips and contractions. So termination of scaling of a, let's say, of an ample divisor. So if, I guess the, the conjecture I just erased. So if you assume termination, so if you just assume that whenever you have a pair like this, foliated, yeah. So I guess, foliated. We could also, just for algebraically integrable foliations, yeah. Also, if you assume the full termination conjecture for varieties in dimension the rank of the foliation, you could get this. But you'd have to assume some termination with scaling thing in our result. But then, termination with scaling, then was proven by Liu, Meng, and Shi, and so Jihao is in the audience here too. So they actually proved termination with scaling in this setting. And as a result, we have an unqualified, so as a result, and what they showed then, is that we have an unqualified contraction and flip theorem. Unconditional, yes. So yeah, maybe, yeah. I'm unqualified to be talking about this, maybe. Yeah, this is unconditional, without qualifiers. I guess I want to make a remark. So to go back to maybe some kind of mysterious mantra I kind of, said to Dan earlier. So I guess I'll just say there are strange features of singularities of even algebraically integrable foliations. From the perspective of the MMP. So just to say some words, a foliation will usually have infinitely many log canonical centers, whatever this means. But I guess you can believe that if you have infinitely many of something bad, this is probably a bad thing. So I just want to emphasize that there are strange things about foliation singularities. from the perspective of the MMP. And so I want to emphasize that Liu, Meng, and Xu circumvent these issues by working with what are called generalized pairs. Now, defining what all this is of course, would take us way too far away, but I just want to emphasize there is somehow this broader framework that we should be working in, and I think the work we've done with algebraically integrable foliations is kind of good evidence that this is a very natural framework for working with foliations, so this broader context of generalized pairs. But again, I don't want to get too into the weeds other than to say that this framework exists, and it seems to address a lot of the problems we come across. So I'll say one more important corollary of this, and then I'll try to prove something. But while I rearrange boards, are there any other questions? Yes, please. Yes, yeah. Or well, when the KF is big, or you have a big boundary. So you need some bigness somewhere to work with. Yeah, thank you.
And do you actually need the canonical, or everything works for log canonical?
So actually, yeah. So all these statements that I'm writing work with F, a log canonical pair. Yes. So yeah, actually, yeah, you could. Yeah, so you could take X. Actually, you could even drop Q factoriality. It turns out. You just need potentially KLT and F delta to be log canonical. So there's a, yeah, this is, we really can do everything for log canonical. So another important trick, I guess, is to observe so notice that if KF is not Ceph, so it's not pseudo-effective, then if A is ample, then KF plus some small amount of TA is not pseudo-effective. So if KF is not pseudo-effective, we can perturb by a small amount of amplitude. It stays not pseudo-effective. So if KF is not pseudo-effective, we can always push ourselves, treating this as our boundary, we can always push ourselves into the regime of a big boundary, and so we can apply termination with scaling. So I guess another corollary that follows from Liu, Meng, Xu is that if KF is not pseudo-effective, there exists some MMP which terminates in the fibration case. So, and again, to emphasize, this is an MMP with scaling of something. But what we scale with isn't so important. So X prime Z such that minus KF prime is F ample. So again, just to recall, this was our case 1 situation. So we know that if we have an MMP which ought to end up in a case 1 situation, we can always get to some case 1 situation. So in some sense, so again, we can always find, just to use some more lingo, we can always find a Morey fiber space structure for a foliation. Okay. And again, these results are in all dimensions. So for algebraically integrable foliations in all dimensions. And so I think this gives some very good and compelling evidence why we might believe this whole story works in full generality. So I have 15 minutes remaining. I want to give just a taste of how proofs in this whole theory work. So I haven't really given you an actual proof over the course of these lectures. So I'd like to give just at least a taste of how we prove things in some cases, and some of sort of the yoga and tricks we use to think about problems. And I wanted to do this by giving a proof of the cone theorem, say for algebraically integrable foliations. But before I do that, I guess I just want to see if there are any questions before I go on with the proof. So I'm going to turn away. So this is the end of me stating nice results about what we do and do not know, and now I'm going to try to prove something. Okay, so the cone theorem, what we need to the cone theorem is something called bend and break. And I think if you haven't seen bend and break before, it's an amazing result. So maybe because it deserves to be up on the board as long as possible without fear of being erased, I'll write down bend and break on this board here. So bend and break has a long history. So of course there's Mori, was the first one to prove some of these results. The form I'm going to be using is due to Miyoka, and then also, I guess the actual form I'm going to write is a version of it due to Kiel, Matsuki, and McKernan, roughly, or adapting Miyoka's proof and their techniques. We prove something like the following. So let d1 through dn be Neff divisors. And I want two things to be true. I want d1 intersecting, and I guess so n here, of course, is the dimension of x. I want d1 through dn to have 0 intersection. So we take the intersection product of all these Neff divisors, we get 0. And I want minus k of f dotted with d1 dn to be positive. Then through a general point x and x, there exists a rational curve L of x passing through x, which is tangent to f. So 1, it's tangent to f. And 2, it has 0 intersection with d1. Oh, yeah, how about that? Yeah. Good call. Let's just say this. Thank you very much. Yeah. Okay, so in other words, if we have some very, I guess, natural conditions, some very natural geometric conditions, and I'll explain exactly how I use this in a second, we can produce lots of rational curves tangent to the foliation. This is a big deal. So I guess I want to remark is that actually this is okay for arbitrary foliations. So not necessarily algebraically integrable on varieties of any dimension, on normal varieties of any dimension. Nothing about singularities. Yeah, so I'm making no assumptions about singularities of either f or x other than normality. And yeah, I'm not assuming anything about algebraically integrable, nothing about dimension, nothing. So this is a very, very general statement. Okay. So how does the cone theorem work? So we're going to basically, the cone theorem, the proof of the cone theorem is basically induction and bend and break. This is how we're going to do things. So just to again, I wish I had more time to talk about bend and break, but please come up to me afterwards and ask me about it too, because there's a lot more to be said. So let's let R inside any x be a kf negative extremal ray. So let's say we have our pictures of this. So this is like a slice of our cone, and so we're taking like a two-dimensional slice of our cone, and this point is our ray here. Now, because it's extremal, actually I'm lying a bit about convex geometry here. So if you know something about convex geometry, don't call me out, but I am lying a bit, but it can all be made okay. There exists what we call a supporting hyperplane. So we can find some divisor, HR. So this is going to be, it's actually an R Cartier divisor, so there's a bit of subtlety here. But so HR is a Neff divisor, or a Neff cohomology class, which is 0 only on R. And the game that we're going to play is we're going to analyze HR. Now, because R is KF negative, we actually know that we can write R as KF plus A, where A is ample. So again, this is Kleiman's criterion plus a little convex geometry. Okay, so if you just grant me that, that this thing exists, we're off to the races. So while I bring down the top board, are there any questions about our basic setup? So again, I've chosen my extremal ray I want to analyze, and I found this supporting hyperplane to it, which is some Neff guy, which I write as KF plus A. So now there are two possibilities which we have to analyze separately. So there are two cases. Either HR to the n is 0, so its top self-intersection is 0, or, well, because Hn to the R is Neff, it's always non-negative, so there are two possibilities. It's either strictly positive or it's 0. Again, this is just because I'm just using the fact that HR is Neff. Okay, so I'll come back to this in a second. I'll handle this case first. So Hn to the R is 0. So let D be the largest, or maybe I'll call it, let nu for numerical dimension. I mean, nu is the numerical dimension of HR, so it's the max D such that Hn or HR to the D is not equal to 0. And the idea now is you apply bend and break with the following divisors. So take D1 up to D of nu plus 1. You take these to all just be HR. And you take D of nu plus 1 all the way up to Dn to be A. And so clearly, again, by definition, we have that D1 up to Dn has to be equal to 0. But now minus Kf dotted with D2 dotted with, Dn is just equal to A dotted with D2 to Dn, which is positive, again, by definition of nu. So both of these hold by our choice of nu. So namely the numerical dimension. Yes, thank you. Yeah, man. You saved me twice on that. Yeah, nu plus 2. Brilliant. And so that means there exists an Lx such that Lx dotted with d1 is equal to 0, but this is just Lx dotted with hr. But hr is 0 only on R. So Lx has to be, its class has to be in R. But this implies that the class of Lx, or maybe I'll just call it L because I don't need to worry about the x so much. This implies that L is in R. Again, recall that HR is 0 only on R. And that was the curve we were looking for. So again, this is a very clever application of bend and break. Let's see here. So now it remains for me to consider the case where HR is not 0. And this is where the inductive step happens. And so we'll see. So if HR to the n is bigger than 0, well, this implies that HR is big. In other words, we can write HR as being, well, numerically equivalent to an ample divisor plus some effective divisor, E. So A is ample and E is effective. And this is, I guess, Kodaira's lemma. That this follows. So if HR to the n is positive by Kodaira's lemma, we can really write it as an ample divisor plus an effective divisor. But A dotted with R is positive because A is ample. So this implies that E dotted with R has to be negative. So in other words, this implies that if T to X is the normalization of the support of E, then R is contained inside the image of the natural map any bar T. So image any bar T to any bar X. So in other words, R is coming from some lower dimensional subvariety. So maybe because I'm quickly running out of time, I'll just say that this is where the induction happens. So maybe I'll just say what the key ingredients are. So now we want to apply induction on dimension by considering the restriction of f to t. So we can pull back the foliation to t. So the key ingredients in doing this are, one, we need some sort of adjunction formula. In other words, we have to relate kf to the pullback kft. So we need some way to compare what these two divisors are. So if you're familiar with the junction formula for varieties, which I assume most of us are, there is a similar formula for foliations, which allows us to write kf and kft in the pullback foliation. And then 2, and this is the very subtle part of the whole story, which I won't be able to say more about, is we need to control the singularities of T and Ft. And this is really the hard part of the whole story in the induction setup, is controlling these singularities. But it can be done through through sort of some interesting techniques on partially resolving singularities. So maybe I'll just say the words DLT modifications. But just to say that there's something that one can do, and really you need some sort of foliated version of DLT modifications. Okay, so I'll end there and not give any more details of the proof, but again, if you want to know more details, please come up and talk to me. I guess the one thing I want to say, I guess if you'll permit me just a few more seconds. So Charles asked a very pertinent question last time, like, what's the point of all this? Like, so I mean, not to call you out, but yeah. But yeah, so like, why bother? I mean, we've gone deep into the woods of the mineral model program, and so like, what's the bigger picture here? Why, where do we go from here? So I just want to maybe make a few quick statements about why we did all this. What was the point of trying to make KF-NF? So one reason is special metrics. If we want to find a special metric on our foliation, in practice, we need to make KF-NF. So this is the first step to finding special metrics. So if you care about special metrics on foliations, this is a necessary first step to doing this. Another big problem is the finite generation, studying the failure of finite generation of this ring. So Roberto talked about this. I briefly alluded to it last time. But this ring of sections is an important ring for various reasons. This is a very important ring to study. It's not always finitely generated. We'd like to know when it is finitely generated. Making KF-NF, again, is a first step to answering these finite generation questions. The final thing, I guess, this is a bit vague, but partial resolutions. So the MMP gives you access to clever ways of partially resolving singularities. So again, I'll just again throw the word DLT modification. This is a powerful technique, and it's only possible because of the MMP. And then the final thing, again, Roberto alluded to this broadly, or briefly, is moduli. So if we want to produce a moduli theory of foliations, a necessary ingredient in producing moduli of foliations seems to be the mineral model program. Okay, so this is sort of just a sampler of some of the bigger picture of why we went through all this effort. But I'll end here, and thank you very much for your attention.
Questions?
Yes?
You advertised some geometric consequences of the foliated structure.
Yeah, so if you, so there's this whole theory of canonical bundle formulas. So if you have, say, so if you have a Calabi-Yau fibration, what you should write is you should write k of x as the pullback of k of z plus some discriminant divisor plus some moduli divisor. And so what we expect is that this moduli divisor is the push forward of an F class. So it has some positivity properties. So actually, we were able to do a few things along these lines. One, using these techniques, we're actually able to prove these kind of results when you allow worse singularities on the fiber. So normally, proving this, you prove this as Neff by using some Hodge theory techniques. But that kind of constrains the kind of singularities you can work with. By using foliated techniques, you completely circumvent the Hodge theory techniques, and you're able to work with a broader class of singularities. The other thing is, and this was one of Shakurov's insights, is that you can actually make sense of the moduli part. So you can make sense of moduli part for general fibrations. And this was sort of our initial motivation, was to study the moduli part of a general fibration. Those are Shakurov's observations. You can do this much more generally. And so Shkurov had some conjectures about the properties of this moduli part, namely that it's Neff, or it has these Neff property, this Neftness property. And that's what we were able to prove actually, is that this general moduli part had the sort of Neff properties that you'd expect from the sort of usual canonical bundle situation. So this was our initial motivation, yeah.
So just to come back to this, I have a vague memory that it's more or less conjecture that this has to be semi-ample on some model. Do you have any hope that using foliated techniques you could achieve that? Or
so if
closer?
if I had to speculate, my feeling is that because finite generation usually fails for foliations, I would be suspicious. I mean, I'm always hopeful, but I'd be suspicious that we could use foliated techniques because abundance is so tricky for foliations. It would be like, kind of doing things in the wrong order, I would guess. That's just my feeling, but I would love to be proven wrong. So maybe I'll try to lead on a hopeful note, but yeah, thank you.
More questions? Okay, if not, let's thank the speaker again.
Thank you.